Okay guys, what we're going to be looking at now is not square root functions, but cube root functions. So we're going to be looking at the function y equals the cubed root of x. Since it's the cube root, I have that little 3 in the ditch. I can write it right. There we go. The cubed root of x, okay? I want to first go through these points with you so that you get a good idea of what the parent graph looks like. So look at the chart on the left of the graph. It is an XY chart. I'll just try to draw it over here. It's an XY chart. And it has the values -8, -1, 0, 1, and 8. Okay, so what we're going to do is we're going to form our parent graph of the cube root of x using this chart here. Let's start with -8 because it's all the way to the left. I have 1, 2, 3, 4, 5, 6, 7, 8. What is the cubed root of -8? Well, I know you guys know that the cubed root of 8 is 2. And so the cubed root of -8 would then be -2. And you can check that because, let me do a little side work here. I'm trying to get -8. So I got -2 times -2 times -2. I know that gives me +4. But if I multiply that by -2, I get -8. Okay, guys? So, cubed root lets us do, root of negative numbers because it's cubed and it's odd. If it were even or square root, that wouldn't be possible. Because we can't take the square root of negative numbers, but we can take the cubed root of negative numbers because we just saw y. So, the cubed root of -8 is -2. I'm going to go ahead and draw that point on my graph. I've got -8 and -2 right about there. What's the cube root of -1? Well, again, I have -1 times -1 times -1. That gives me -1. So the cube root of -1 is actually just -1 again. The cube root of 0 is 0. Any root of 0 is 0, or any power, 0 to any power is just 0. The cubed root of 1 is +1. And the cubed root of 8 is +2, because these numbers are positive. Okay, the cube root of +8 is not -2, it's 2. So let's graph these. So I've already graphed that guy. Now let's graph -1, -1. Just right, which is right there. 0, 0, right there. 1, 1, right there. And 8, 2. 1, 2, 3, 4, 5, 6, 7, 8. Up 2, right, right there. Excuse me. Okay, so I'm just going to go ahead and trace out my graph. It looks like it's looking something like that. Now let's talk about the graph. What is going on here? Well, our point of inflection. That means where is the graph changing, whether it's increasing or decreasing. Okay, so it looks like the graph is increasing all the way up to there. And then once I pass that point, actually, no. The point of inflection is not where it's changing, increasing, or decreasing. It is where I see that shift here. Okay? So that is the point of inflection, is where I see that major shift right there. There's probably a better way to explain that. I just can't think of it right now. So that point is at 0, 0. Okay? Right here is when the graph changes. Okay, here's the way that we can think about it. Up until I reach 0, 0, the graph is starting to look like a smiley face, right? I mean, not fully like a smiley face, but it's more concave up, what we say. Once I reach 0, 0, it's going to start looking more like a frowny face. I mean, obviously it's increasing very slowly, so it's going to be like a really wide frowny face. But that's only after I pass 0, 0, and we say that it's concave down after that. So my point of inflection is where it changes from looking like smiley face to looking like a frowny face. And I can see that that is actually just right at 0, 0. I'm going to undo this mess since I've explained what the point of inflection is. I think we all get it. It's at 0, 0. So let's look at a couple more things about this graph. We said its point of inflection was at 0, 0. Its domain, well, the graph never stops on the left. We can always take the cube root of negative numbers. So it looks like I can be existing all the way up to negative infinity. And it's never going to stop on the right either, because we can always take the cube root of positive numbers. So it's going to exist all the way to infinity. So that's my domain, negative infinity to infinity. The range is actually the same thing. I mean, the graph just keeps going further and further down the y-axis as I go farther out. Even though it's going down real slow, it's still going to go further and further down the y-axis. And as I go further to the right, it's going to go further and further up the y-axis. Even though it's going real slow, it's still going further and further up the y-axis. So this is actually both my domain and my range. What is my interval of increase? Well, something that we have to notice here is even all the way to the left, I mean, the graph is only moving up. It's just slowly moving farther up and farther up and farther up. It moves a little bit steeper over here. But then as we keep going to the right, it's still moving up. So it looks like the entire interval from negative infinity to infinity is my interval of increase. My interval of decrease, well, the graph is actually never decreasing. It's only moving up. It only has a positive slope. My end behavior, okay, so what's happening as x approaches negative infinity? Let me make it a little more cleaner so we can talk about that. Alright, what's happening as the graph approaches negative infinity? So what's happening as x approaches negative infinity? What's happening to y? Well, y is only going to get more negative as I keep going to the left. So, as x approaches negative infinity, so does y. Y continues to get more negative as well. Y approaches negative infinity. And what happens as I move to the right, as x approaches infinity? Well, as x keeps going in the positive direction, so does y. Y is just going to get bigger and bigger, so y approaches infinity. So that is my full analysis of this graph, okay? Now, let's use what we know about all this to go ahead and graph our parent function. Or not our parent function. To graph a new function. Actually, I'm going to do that in another video because I want to save all this work that I did. So, stay tuned and I will graph a new function using the parent graph of y equals the cubed root of x to graph a new function using transformations just like we did for the square root.